Hi everybody. Good morning or good afternoon, depending on wherever you are. Today I'll talk about our work, DeepEdge, which is an efficient framework for deep learning model update on heterogeneous edge. I, Anirban Bhattacharjee, and my colleague Ajay Dev Chokra contributed equally in that paper. In that paper, we will discuss how to run deep learning model retraining efficiently on the heterogeneous edge devices where computational power varies significantly among devices. Moreover, the edge devices are deployed to serve latency critical jobs. We intend to run deep learning training jobs on the spare resources of the edge devices without violating the SLO or service level objective of the running jobs. So here in that paper, I'll first introduce the topic, then I'll go through the requirement and challenges for our work, then I'll talk about the design details of the deep edge, and I'll talk about evaluating our deep edge framework using real world data, and then finally I will conclude our talk. Let's dive in. Machine learning or deep learning models used nowadays for various purposes like stock prediction, autonomous vehicles, malware or fraud detection, NLP speech recognition, etc. Deep learning models are trained once on a specific dataset, then that is used to classify or predict unlabeled data as new requests come. And now, when these models are deployed on the production environment because of the new data or new data patterns, the model degrades over time, which is known as concept drift. And then we have to update the models to gain the accuracy again. And that motivates the scenario to do the model update. The deep learning training time and cost depend on the transfer cost of data from the source to the execution environment and the computational power of the executional device. As we all know, the cloud has enormous power to execute the deep learning training job efficiently. However, the data transfer to the cloud from the edge devices is a significant communication overhead, and there are some privacy concerns. With the advent of GPU-enabled edge devices, we can now do the model update on the edge devices. Moreover, deep learning model update is a resource-intensive task, so if we can distribute the training workload among multiple devices, that is beneficial.
Now, let's discuss about the requirement and challenges for our work.
Now, before diving into the challenge section, I would like to introduce the deep learning training procedure. Deep learning neural networks usually represented as a graph network. Then we initialize weights randomly or transfer weights from previously learned tasks of a similar network on each of the graph nodes. Then during forward pass, neural network predicts the y hat, which is the predicted value, based on the current weight w and the inputs. Then we calculate error between the y hat, which is the predicted value, and y, which is actually the ground truth value. Then during backward pass, we calculate the gradient of the error with respect to weights. And based on that, using some optimization function, we update the weight of the graph nodes. The forward pass happens on each input data points, but to make the training procedure more efficient, the backward pass happens on the chunk of data which is known as batch. So basically, the backward pass happens on the chunk of 64 data points or 128 data points, like that. And whenever all the data points are covered by the neural network layer on a single pass, then it is known as one single epoch. And the epoch repeated multiple times, like 100 times, up to the point the desired accuracy is reached. Now, as a first challenge, in the distributed deep learning training, there are multiple parallelism technique and there are multiple architecture exist in the literature. Which one to choose? So here, the main two parallelism techniques are model parallelism and data parallelism. In model parallelism, the deep learning model is distributed among multiple worker nodes. But in our work, the model can fit on a single worker node, so we didn't opt for model parallelism in our work. For data parallelism, on the other hand, there are two architecture exists. One is decentralized architecture and another one is centralized architecture. On the left-hand side, you can see here for the centralized parameter server architecture, there are multiple worker nodes exist and the centralized part of that architecture is the parameter server. Here, each worker node has the same model replica, but it operates on the not on the whole dataset, it operates on the shard of the whole dataset. During forward pass on its individual data shard, which is non-overlapping data shard, it calculates the error function, and based on the error function, it calculates the gradients during the backward pass. And then after each worker node calculates a gradient, it sends the gradients to the parameter server, and then the parameter server uh, uh, calculate the weight and push it back to the worker node again. And that's how the deep learning training procedure progresses on the data parallelism centralized parameter server architecture. However, there are two ways to do parameter synchronization on the parameter server. So basically, during the synchronous parameter synchronization, each worker node calculate its gradient on individual worker node, send it to the parameter server. The parameter server waits till the point all worker nodes send their updated gradients. And whenever all worker nodes send their updated gradients to the parameter server, it calculates the weight and send it back to the worker nodes. So here, if there is any straggler worker node, basically for that the parameter server waits till the point that worker node actually successfully sends the gradient to the parameter server, which can delay the whole procedure. And during the asynchronous parameter synchronization, which is another technique, the parameter server doesn't wait for each individual worker to send its updated gradients. Whenever individual worker sends the gradients to the parameter server, it calculates the weight and sends it back to the worker node. Then whenever the next worker node comes, it sends its updated gradients and it calculates the parameters on the parameter server and send it back to the worker node. However, this technique can delay the model convergence, so the accuracy to reach the desired accuracy, the whole deep learning model can take more epochs. And other than that, there is another architecture called decentralized architecture. It incurs huge amount of communication between the worker node, and if the worker node are heterogeneous, then it can delay the whole procedure. So based on our scenario, we selected asynchronous parameter server synchronization technique with decentralized parameter server architecture for our work. So let's
Now, for the second challenge, I'll speak about how heterogeneity plays a role here. Here on the left hand diagram, you can see that a TX2 device is much faster than nano device. And because of that, if we share the data equally among devices, then the TX2 device will complete processing the data per epoch much faster than the nano devices. However, after completing one epoch, it will not forward because it has to wait for all other devices. Now I'll talk about how deep learning training jobs can exert pressure on the background latency critical jobs, and here you can see that how the CPU, GPU, memory utilization of the whole resources is increased because of running the deep learning job, and if that goes beyond some threshold, then it will lead to the violation of SLO for the latency critical job, which is not desired. And moreover, if we run the run the deep learning job co-located with the latency critical jobs, it will also sensitive to the background jobs, and here you can see the deep learning training time increases by 20% if we run it co-located with the background jobs.
Now I'll talk about how we formulate the problem statement. So yeah, basically we formulate an optimization problem to optimize model update time while guaranteeing SLO of the latency critical jobs. Here we employ one deep edge manager which is responsible for sharding the data among the workers. The transfer cost is basically the time taken to send the shard from data source to individual workers. The T compute time is the time to do the forward and the backward pass, and T update time is basically to push the gradients to the parameter server to update the weights in the parameter server, and the to pull the weights back to the individual worker nodes. Initialization cost is the time taken to start the deep learning model update job, and the total cost is a summation of the max of transfer cost, max of initialization cost, and max of epoch time among workers multiplied by number of epochs to reach the desired accuracy level. Now we formulate the optimization problem to minimize the total cost, which is subject to some constraints. One is batch size should be in a specific range, and the B max, which depends on the available memory of the worker node. And for each worker W, the pressure which is exerted by the model update job on the background application should be inside some threshold. Otherwise, if that is beyond some threshold, then the SLO of the background latency critical job would be violated. Now I'll talk about the design and implementation of the deep edge framework. Now this section is divided into three parts. One is system architecture, then the model for workload distribution, and key ideas and evaluation result. Deep edge comprised of multiple worker nodes, one data source, and one parameter server, and we have a deep edge manager, which has 5 components: profiler, resource monitor, sulfur, launcher, and accuracy monitor. And all the worker node parameter server source deep edge manager is connected by a Ethernet switch. Now we'll talk about the model for workload distribution. So our model for workload distribution estimation is divided in two phases. One is offline phase, where we do the profiling and performance model learning, and on the online phase, we actually do the workload distribution estimation. So here, first in the offline phase, we basically start the stressor. We get the initial state of each individual worker node. Then we run the deep learning target application on it, and then we monitor all the resources along with CPU, GPU, memory, and we also monitor the T compute time, which is the forward pass, backward pass summation time, and T update time. And finally, whenever those are done during the individual process, we kill the stressor and then finally terminate the application. And next, during the online phase, here first, whenever the model degrades beyond some threshold, then the model update is triggered. And then based on that worker node, then we have our algorithm which decide the data shard size among the available worker node. And now the data store actually sends the sharded data among the worker nodes. And whenever the worker node receives all the data points, then the launcher starts the deep learning training job among the worker nodes. And then the accuracy monitor monitors the accuracy after each individual epoch, and whenever it reaches the desired accuracy, then the deep learning model job is terminated. And now I'll talk about the evaluation result. Here our test bed comprised of 3 NVIDIA Jetson Nano device, one TX2 device, one Raspberry Pi device, and all of that is connected by a 1 gigabit switch. Our workload is a Caltech dataset, and we trained our base model with 2570 data points. And whenever it reaches 75% accuracy, then we consider it as our base model. And then we pass the Caltech dataset individual data points to our trained model. And whenever the accuracy degrades beyond 50%, we triggered the deep learning model update. And we used MXNet as our deep learning framework.
So for our evaluation, we run the deep learning model update by stressing different dimensions of the resources. The dimensions are CPU, GPU, memory, etc. And we calculate the T compute and T update time on the resource stress condition to build our machine learning profiler. So here you can see, like, stressing the GPU increase the compute time, increasing number of workers also increase the update time. Here increasing batch size decrease compute time, and decreasing batch size increase update time. And here for parameter server, if we increase the initial CPU usage in the parameter server, that increases the update time. And here we jot down all the observation for our sensitivity analysis. Now, by logging all the data from our sensitivity analysis and pressure analysis, we create our performance model, which is basically a machine learning model which can predict the estimated compute time and estimated update time based on the current state of the devices. And here you can see that we use H2O AutoML XGBoost machine learning model to predict that estimated compute time and estimated update time on individual resources. And now we also do it for our pressure analysis. So basically here we estimate that if we run deep learning job, and if that is the initial state of the resources, what will be the final state after running the deep learning model. And now here we evaluate our data sharding strategy. We update our model based on 4600 data points, and in which 3855 data points are used as the training points. And based on the current state, we divide the data points among the individual workers. Here you can see that for the first model, we gave 1893 data points to the TX2 and 654 data points to the nano devices. And then the epoch time was 121 seconds among the 4 nodes. And if we use 3 nodes, then 1 TX2 device and 2 nano devices, then the TX2 we gave 2281 data points, and for the nano devices we gave 787 devices, but the epoch time was 148 seconds. So basically, if we use 1 TX2 device and 3 nano devices, the epoch time was minimal, and that's why we, in that case, we consider 1 TX2 and 3 nano devices configuration. And here you can see that our scheduling strategy is 1.54 times efficient than if we give equal amount of data to the individual nodes. And here the red points shows divide the data points fairly among individual workers, and the blue points shows how deep edge performed. And here we also show that even if we change the batch size and even if we shard the data based on our data sharding strategy, the model still converges, and that validates that our strategy also meet the goal for the model convergence. Now I'll summarize our talk by saying that we built a performance model to estimate the pressure and sensitivity to run a deep learning model update with background latency critical jobs. We also create a data sharding strategy and we evaluated deep edge and showed that our strategy reduced the model update time while guarantees the SLO of the latency critical jobs. And here we want to thank all our funding agencies. And that concludes my talk. Now, if you have any question, please go ahead. Thank you for listening to my talk.